All right. So what I want to do is our primary topic today is about solution concentrations, and that's going to lead us into Friday where we talk about solution concentrations and chemical reactions, doing solution-based stoichiometry. Before I do that, though, let's take one more example. This example was not in either of the YouTube videos. This example was not on your page. But let's go ahead and do this one together. And while you're figuring out your style still, let's go ahead and do this one in the mode of the half reaction method, since we already did an example together in class using the oxidation number method. When we're doing the half reaction method, the half reaction method does have some advantages to it. One of those advantages is that I don't have to do anything with oxidation numbers. I don't have to break out my algebra. I don't have to do any math. I can just kind of focus on the half reactions themselves. And so what we look for in the half reaction method are pairs. So I've got the manganese pair here, and I've got the carbon pair here. Those are going to be the bases of my half reactions. My first half reaction, I'm going to have the permanganate ion turning into the manganese 4 oxide. And I'm going to have in the second half reaction, the oxalate ion turning into carbon dioxide. Those are my two half reactions. Now, at this point, I don't know which one is oxidation and which one is reduction. That will come out as I do the balancing. But those are my two pieces. Now, the half reaction method can be broken down into these steps, and I'll type them instead of writing them. That'll make it a little bit easier to read. The first step is to balance the non-oxygen and non-hydrogen elements. Second step is to balance oxygen with water. The third step is to balance hydrogen with H+. So for each half reaction, I have to do these 5 steps. I have to balance the non-oxygen, non-hydrogen elements, balance the oxygens with waters, balance the hydrogens with H+, balance the charges with electrons, and flip if it's a base. I'll talk about what that last step means in a minute because this one is in base and we'll have to do the flip. So let's start with the first. The non-oxygen, non-hydrogen in the case of the first half reaction is manganese. I've got one on each side. It's already balanced. So check that one off. Second one, balance oxygens with waters. I've got 4 oxygens over here but only 2 over here. So I need 2 water molecules to balance that out. My next step is to balance hydrogens with hydrogen ions. I just added 4 hydrogens to the product side, so I'm going to need to add 4 hydrogen ions to the reactant side to balance them out. The last step is to balance the charge with electrons. I need to evaluate each side of the reaction. I have a -1 and 4 positive ones. -1, -1 plus 4 is equal to +3. On the other side of the equation, I have no charge in the manganese 4 oxide, no charge in the waters, so no charge overall. Now we're balancing charge with electrons. Electrons are negatively charged. So we need to add them to the side that is more positive to make it more negative, to even it out. So the more positive side is this side. How many electrons do I need to turn that +3 into a 0? 3. So there's my balanced half reaction for the manganese half reaction. Now, this is an acid reaction. And the reason we know it's an acid reaction is the presence of that H plus there. We're asked to balance this in base. This is where we have to flip. Now, what do I mean by flip? Those 2 things that we added need to switch places. We're going to flip the waters and the hydrogen ions in terms of their sides of the reaction. And while we do that, we're not only going to flip it, we need to convert those hydrogen ions into hydroxide ions. So can you see what I did? The 2 waters that were product are now 2 waters on the reactant side. The 4 hydrogens that were on the reactant side are now 4 hydroxides on the opposite side. I have effectively flipped the hydrogen and the oxygen substances. That is my balanced half reaction for this equation in base. Now we can double check ourselves, make sure that it meets all the criteria. Is it balanced atomically? Is it balanced by charge? Well, I've got 1 manganese on each side. Good. I've got 4 plus 2, that's 6 oxygens. 2 plus 4, 6 oxygens. I've got 4 hydrogens and 4 hydrogens. All my atoms are balanced. From a charge standpoint, I have a -1 and a -3 from the electrons. And I've got 4 negatives from the hydroxides. That's all balanced as well. So my half reaction is balanced from all the criteria that we set. Something else that I can do I can look at this and say, okay, I've got electrons that are being absorbed by the manganese. So this is a gain of electrons. By definition, the gain of electrons would be what kind of process? Reduction. Gain of electrons is reduction. Leo the lion goes grr. So we could label this half reaction as my reduction half reaction. And that would mean the permanganate ion here would be my oxidizing agent. By process of elimination, we'll prove this to ourselves later. If this is the reduction reaction, the oxalate must be the oxidation reaction, which would make the oxalate ion the reducing agent. So this method, while longer than the oxidation number method, does allow us to arrive at the same conclusions that we did in the last, where we can identify what's oxidized, what's reduced, what the oxidizing agent is, what the reducing agent is. We can do all of that in this particular method. It just, you have to do a little bit more interpretation. But the upside is I didn't assign a single oxidation number. And for those of you that are struggling with oxidation numbers, that's a really valuable asset. All right, let's go ahead and finish this off. For the half reaction involving oxalate, I've got C2O4 -2 turning into CO2. Part 1, balance the oxygen, the non-oxygen, non-hydrogen. Well, I've got 2 carbons over here. I need to double the CO2 to give me 2 carbons there. In that process, I went from 4 oxygens on the left side to 4 oxygens on the right side. Those are now balanced. I don't have any hydrogen, so I don't need to do that part. I just need to balance the charge. -2 overall on this side means I need 2 electrons on that side to balance it out. I don't have any hydrogens or waters, so I don't need to flip it even though I'm in base. This is the set half reaction. So the only thing left to do is to combine these 2 half reactions to give me the overall reaction. So I started with a full reaction. I split it into halves. Now I need to add those 2 halves together again. But before I do, I have to take care of another issue. The reduction half reaction requires 3 electrons. The oxidation half reaction only gives us 2. I need to get those values to even out with each other. And so this is where multipliers come in. This is where I have to go to my lowest common multiple. Lowest common multiple between 2 and 3 is 6. So I'm going to end up doubling this top reaction and tripling this bottom reaction to get it to work. Now that I do that, now I can combine them. 2 permanganate plus 4 waters plus 6 electrons and 3 oxalates make 2 manganese 4 oxides, 8 hydroxides, 6 carbon dioxides, and 6 electrons. The last step in this recombination is to look for the redox version of spectator ions. That is common things on both sides of the reaction. Your electrons will always be in that camp. Sometimes waters and hydroxides or hydrogen ions will be there as well. You just have to kind of be on the lookout for them. In this case, there aren't any of those because the oxalate half reaction did not have waters or hydroxides. So all that we would have is what's left here. 2 permanganate plus 4 water plus 3 oxalate make 2 manganese 4 oxides, 8 hydroxides, and 6 carbon dioxides. So I've said this a couple of times. This is not my favorite or my preferred method for doing these kinds of reactions. This example took us nearly 20 minutes to do. Now, granted, I stopped and I taught you and explained a lot of things along the way, but still, I could have done this example with the oxidation number method in probably about 2-3 minutes. Even without talking through every single step, I probably would have taken 5 minutes or more to do the half reactions this way. It is a longer process. There are advantages to it, though, as you've seen, in terms of what you're allowed and not allowed to do, what you need to do and what you can do. You can get all the information without assigning a single oxidation number. For some of you, that's kind of a game changer. For others of you, it's not going to make that big of a difference. Some of you are going to gravitate toward one or the other. You just kind of need to decide for yourselves what works best for you. Any questions before we put this away? All right. So the other big thing that we wanted to talk about today was solution concentration. Now, when it comes to solution concentration, we can break down solutions in terms of really 2 different ways of looking at concentration. There is the concentration unit based on mass, and there's the concentration unit based on moles. Now, in both cases, that mass or that moles, those belong in the numerator of the fraction of the equation that we are going to use. Virtually every concentration unit that we can think of is a ratio unit, meaning it's got a numerator and it's got a denominator. The numerator is always based on the solute, or at least 90% of the time is based on the solute. In chapter 11, we'll talk about a unit that actually uses solvent in the numerator. That's kind of a rarer circumstance. Most of the time, it's the solute in the numerator. What's in the denominator? Oh, it depends upon what we're trying to measure. Depends on what we're trying to compare. Sometimes it's solvent. More often than not, though, it's about solution. And today, our focus is really going to be on that. Solution-based concentration units, where we're either going to use mass of solute or moles of solute per some unit of solution, whether it be liters, kilograms, grams, whatever the case may be. So let's take a look at some of those common units. First, this one should look familiar to you. We've done a lot with mass percent. Mass percent of a solution is the mass of the solute, mass of A, divided by the total mass of solution times 100%. Now, I want you to focus in particular on this fraction. This fraction, sometimes referred to as mass ratio, pay special attention to it. Mass of A divided by total mass. Mass of A divided by total mass. Because what we will notice is I'm going to flash two other concentration units here on the board. I want you to tell me, I want you to see if you can pick up the commonalities between them. So take a picture of that in your head. Now compare it here. Mass percent, parts per million, and parts per billion. All three have the same mass ratio as the fundamental cog of their equation. They all have the same thing. We can flip back and prove that to ourselves here. Mass of A divided by total mass. Mass of A divided by total mass. Mass of A divided by total mass. The only thing that is different that separates those three concentration units from each other is the multiplier. In percent, percent means parts of 100. We multiply that one by 100. In parts per million, we multiply that by 1,000,000. In parts per billion, we multiply that by 1 billion. Now, why have three different units that all essentially are calculated the same way? Well, it's relatively simple. It's a matter of concentration. Mass percent, we tend to use for higher concentrations. Parts per million, parts per billion, we tend to use those for lower concentrations. Things where mass percent wouldn't make as much sense. You know, if something's 0.003%, it's a lot easier to say that's 30 parts per million. So the scalar attribute here is all about making numbers that kind of make sense and are easy to digest, easy to wrap your brain around. People do a really lousy job of understanding scale. If I've got a whole bunch of zeros before something, 0.00001 something, or if I got a whole bunch of zeros after something, concentration unit of 200 billion. I have no way of really fathoming what that looks like. But context helps a lot. And that's where these different units kind of come in. Now, with parts per million and parts per billion, in aqueous solutions, we actually have another way of representing these. Parts per million is also known as milligrams per kilogram of solution, or milligrams of solute per liter of solution. And what we're taking advantage of there is the fact that if we're dealing with something aqueous, density is probably pretty darn close to 1, if not 1 exactly. A liter of solution in a low concentration is probably going to weigh about 1 kilogram. And we can make a similar kind of statement for parts per billion. In aqueous solution, ppb, parts per billion, is micrograms of solute per kilogram of solution, or micrograms of solute per liter of solution. Why is that relevant and important? Well, when it comes to doing conversion calculations, we'll find where that's useful to us here in just a minute. But things to kind of log in, keep in mind, that'll help you a lot in that regard. Another common concentration unit is that of molarity. Molarity is the number of moles of solute per liter of solution. Now, molarity units are probably the most common units in our laboratory, and this is because molarity units tend to be used when higher concentrations of substances are present. So parts per million, parts per billion, we tend to see those on the low end side when we're doing things like measuring the contaminants in water or the amount of a particular low concentration ingredient in a building material. Parts per million, parts per billion, we're measuring how many bacteria are in an air sample. Those are low concentration kinds of values. Molarity, on the other hand, is a high concentration value. Molarity and mass percent do often have kind of the same language. They talk to one another in some ways. The lab that you're doing right now, you're measuring both, right? You're doing a molarity of acetic acid in vinegar via titration, and you're also comparing that value to the label value of 5% acidity, which is a mass percent value. Both are used because they're both relevant. Now, with molarity, we understand that molarity tells us that we have, so let's imagine that we have a concentration X molar. What that tells us is that we have X moles of our solute, and that is equal to 1 liter of our solution. Now, why is this particular distinction important? What it allows us to do is, remember, anything that we can tie together with equal signs, we can use in a dimensional analysis unit conversion kind of problem. And so from that standpoint, this allows us to do things like this conversion factor, where I can find how much mass I need based upon how much solution at what concentration I need to make. Molarity times volume in liters will give me moles of solute. If I have that moles of solute, I can convert it into grams the same way I convert everything in grams from moles, by multiplying by the molar mass. So let's take a look at an example. What is the molarity of an aqueous solution prepared by adding 36.5 grams of barium chloride in enough water to make 750 milliliters of solution? All right, for this one, I needed to use my equation. Molarity is equal to moles of barium chloride, BaCl2, divided by liters of solution. Now, we're already told the volume of the solution is 750 milliliters, which would be 0.7500 liters of solution. We just need to figure out how many moles of barium chloride there are in that 36.5 grams. And for that, we do it like we've done all along since chapter 2. We do a conversion between the grams of barium chloride and the moles of barium chloride using molar mass. Molar mass of barium, 137.27, or excuse me, 0.33. Chlorine is 35.45 times 2, since there are 2 of them, 208.23 grams per mole. My grams cancel. I've got left with moles. 36.5 divided by 208.23. I get 0.175 moles of barium chloride. That goes up into my equation now. .175 divided by 0.75 gives me to three significant figures, 0.233 molar barium chloride. So when we are doing these kinds of calculations, it is important to know that our unit has two parts. First of all, it's the unit itself. So the unit here is molar, capital M. But we also have to say what it is molar in. So we need to identify the solute here. So this is incomplete if I don't say that it's 0.233 molar barium chloride. If I just say that it's 0.233 molar, it's implied, but it's not explicit. And we need to be explicit. We need to be specific when it comes to solution concentrations. We want to make sure that we are identifying things correctly, especially when we have the circumstances where we have multiple solutes present in the same solution. We want to make sure that we are identifying them correctly. All right, any questions with example 11 here? All right, example 12. The maximum concentration of vinyl chloride allowed in drinking water is 0.002 milligrams per liter. What is that concentration in moles per liter? Now, based on what we said just a couple of seconds ago, we understand, we recognize that this is 0.002 parts per million. Milligrams per liter for an aqueous solution is the same as parts per million. So what we're really getting after here is we have 0.002 milligrams of vinyl chloride in every liter of our solution. We want to take this to moles of vinyl chloride per liter of solution. And so notice that our denominator is not changing here. All that needs to change is the numerator. I need to convert the numerator from milligrams into moles. This is an easy task. This is nothing new, actually, from what we've had to do in the past. All we are doing effectively is converting milligrams into moles. We just got that one extra little step there on the bottom to kind of keep us confused. So my first step, I want to turn those milligrams into grams. The conversion there is a metric conversion. 1 to 1,000, that's going to turn the milligrams into grams. The next step would be to turn the grams of vinyl chloride into moles of vinyl chloride. Here I need a molar mass, but more importantly, I need a chemical formula. Chemical formula for vinyl chloride is C2H3Cl. So my molar mass, 12.01 times 2 plus 1.01 times 3 plus 35.45. 62.50 grams per mole. My grams of vinyl chloride cancel. I now have moles of vinyl chloride per liter of solution. 0.002 divided by 1,000 divided by 62.5 to one significant figure. I get 3 times 10 to the negative 8th molar vinyl chloride. So this is kind of an illustration. This is why we don't use molar concentrations for things that can be expressed in parts per million or parts per billion. In this case, 0.002 parts per million is 2 parts per billion. And so a 2 part per billion solution of this particular compound has a molar concentration of 3 times 10 to the negative 8th. That number we have nothing that can really fathom what that means. That is a tiny number. That's why we use parts per million and parts per billion for these kinds of solutions. We can contextualize 3 or 2 much better than 0.0000003. All right, questions with this one? All right, last example for the day. We've got an aqueous solution called phosphate buffered solution, PBS. Is used in laboratories and biolabs in particular for storing and washing of living cells. One of the many ingredients in PBS is a 10 millimolar solution of sodium monohydrogen phosphate. What we want to do is we want to know what the concentration is in parts per million. So once again, we have to understand our definitions here. 10.0 millimolar would be 0.0100 moles of our phosphate in 1 liter of our solution. Since this is an aqueous solution, we're essentially reversing the process of the previous example. We want milligrams of our phosphate in every liter of solution. And so that's all that we would have to do is that conversion. So I've got 0.0100 moles sodium monohydrogen phosphate in 1 liter. One mole of sodium monohydrogen phosphate. I'm going to need a molar mass. Sodium, 22.99 times 2. Hydrogen is 1.01. Phosphorus is 30.97. Oxygen is 16, and there are 4 of them. 141.96 is the molar mass. My moles cancel. Last step, 1 gram to 1,000 milligrams. My grams cancel. 0.0100 times 141.96 times 1,000 to 3 significant figures would be 1,420 parts per million of the sodium monohydrogen phosphate So we see again there, we've got a solution that even in the molar concentration, 0.01 molar is not very concentrated. But yet, it's over 1,400 parts per million. And that's why parts per million is just generally not a unit we use for something with a higher concentration. We'd be better off putting this in terms of mass percent. And from that particular standpoint, we'd be talking about a solution that's 0.14%. That's a little bit easier to wrap our brains around. All right, so any questions with this one? All right, let's take a look at where we're going. So on Friday, we're going to talk about dilutions, and we're going to get into how dilutions impact and are related to some things that we can do inside of solutions and how we can quantify reactions in solutions. We're talking in particular about titrations, but also about something we call solution stoichiometry. That is all that stuff that we did in chapter 7 with regard to stoichiometry, getting in and out of moles to do calculations based on chemical equations. We can do the same thing with solutions if we start with molar concentrations of the solution. And so that's kind of the last bridge concept that we'll talk about in chapter 8 before we get into kind of the other parts and applications in chapter 11. Any questions? All right. Have a great afternoon. I'll see you on Friday.